The interstellar object known as 3I/Atlas has captivated astronomers and challenged conventional interpretations ever since it entered our solar system. But one of the most tantalizing and revealing features associated with it was captured in an image taken by the Hubble Space Telescope on July 21, 2025. This image, widely discussed and analyzed in various scientific forums, displayed an extended glow projecting outward from the object in the direction of the sun. At first glance, this might have resembled the activity commonly seen from comets, yet a closer analysis revealed something far more perplexing. The viewing geometry was such that Earth's vantage point was only about 10 degrees away from the direct sun-object line. Because of this alignment, the observed glow, if it were viewed from the side, would appear roughly 10 times longer than it is wide. This 10-to-1 axis ratio is not a trivial characteristic. It directly reveals the intrinsic geometry of a jet being emitted from 3I/Atlas toward the sun rather than away from it. This remarkable detail was highlighted extensively in a paper written in collaboration with Eric Kito, in which we outlined why this sunward-pointing jet is both scientifically peculiar and deeply significant for understanding the nature of this interstellar visitor. When the Hubble image was first publicized, experts in cometary science responded with enthusiasm, assuming that the glowing extension indicated ordinary comet-like activity. From the perspective of those familiar with the behavior of comets within our solar system, such a glow typically arises from the sublimation of volatile materials that release gas and dust when heated by sunlight. These gases then stream outward, dragging particles with them. So many astronomers initially greeted the Hubble data as confirmation that 3I/Atlas behaved similarly to a comet. However, this excitement overlooked a crucial and shocking detail embedded directly in the image. The glow was not a tail pointing away from the sun as expected, but rather an anti-tail, an extension projecting toward the sun. Grasping the full meaning of this observation is akin to noticing something in plain sight that completely contradicts assumptions. It is like photographing an unknown animal in your backyard and having your family confidently insist it is just a common street cat, while the photo clearly shows something anatomically impossible, such as a bright tail emerging from its forehead. In other words, the image itself contradicts the familiar category into which one might instinctively place the object. Very few attempts have been made to properly explain this paradoxical feature, and the only serious effort to address this anomaly remains the analysis presented in the paper I co-authored with Eric Kito. Comets traditionally exhibit dust or gas tails that always point away from the sun. This is because the solar radiation pressure and the solar wind, the flow of charged particles emitted from the sun, push the material outward. The physics behind this phenomenon are well established. Sunlight exerts pressure, and solar wind particles impart momentum to dust grains, forcing them in the anti-sunward direction. For familiar comets, the dust tail lags behind the comet and flows outward, creating the classic image seen in astronomy textbooks. Therefore, when encountering an object that seemingly exhibits the reverse, a tail pointing toward the sun, the first expectation would be that something is being misunderstood. If the jet coming from 3I/Atlas contains solid particles typical of comets, especially refractory dust grains capable of scattering sunlight, then such particles should have been pushed away from the sun relative to the object's massive nucleus. This is not a matter of speculation, but a direct consequence of radiation physics. Larger particles, those with sizes of hundreds of micrometers, are less influenced by radiation because their surface area relative to their mass is smaller. However, they also scatter less sunlight, meaning they would not contribute substantially to a bright, visible jet. Conversely, the particles most efficient at scattering sunlight, those comparable in size to the wavelength of visible light, about 0.5 micrometers, would be strongly pushed away by the solar radiation pressure. These particles, if present in a jet, should appear clearly displaced behind the nucleus, forming a typical anti-sunward comet tail. Yet, the image of 3I/Atlas revealed no such displacement. Instead, the bright extension was sunward, a configuration entirely at odds with how dust-laden cometary jets behave. Historically, astronomers have occasionally documented what appeared to be sunward-pointing structures in comets, known as fictitious anti-tails. These, however, were not real jets or emissions directed toward the sun. Instead, they were illusions caused by geometric perspective. When Earth crosses the orbital plane of a comet, observers may temporarily see the dust trailing the comet from a particular angle that makes it appear sunward. In reality, the dust still lies behind the comet in its orbit, but the alignment between Earth, the comet, and the sun creates an optical configuration that tricks the eye into perceiving a forward projection. Several documented cases of these illusions exist, and they are well understood examples of how three-dimensional structures can be misinterpreted when viewed from a particular line of sight. But this known explanation is definitively not applicable to 3I/Atlas. In the case of this interstellar visitor, the anti-tail observed was not a perspective artifact, but a genuine physical extension toward the sun. At the time of the observation, the object was far from the Earth-Sun line crossing, and its trajectory indicated that it was moving in the direction of the jet, toward both the sun and Earth, making geometric misinterpretation impossible. The structure is therefore unique and real, not an optical illusion. The mystery deepened further when a new image was reported from the 2-meter twin telescope, TTT, an instrument consisting of two pairs of 0.8-meter telescopes located at the Tide Observatory in the Canary Islands, Spain. This image, composed of 159 exposures of 50 seconds each and taken on August 2, 2025, revealed once again a faint jet extending toward the sun. Despite being fainter than the bright glow captured by Hubble, the structure retains the unmistakable sunward orientation that defies traditional cometary behavior. The jet reaches a projected distance of approximately 6,000 kilometers from the nucleus, consistent in scale with the earlier detection. The repeated observation of such a feature from two different instruments, at two different times and under different viewing geometries, reinforces the conclusion that 3I/Atlas is exhibiting a genuinely anomalous form of activity. This recurring anomaly prompts deeper questions about the composition, behavior, and physical mechanisms operating in this interstellar object. If the jet is not composed of dust particles typical of comets, then what is it made of? What mechanism could propel material sunward against the force of solar radiation pressure? Could the jet be driven by gas dynamics rather than dust, perhaps involving molecules or atoms with properties unlike those familiar from solar system comets? Alternatively, is 3I/Atlas composed of fundamentally different materials, originating from a planetary system unlike our own? The sunward jet suggests either an emission process capable of overcoming solar radiation pressure, or more intriguingly, particles that do not interact with sunlight in the typical way. If the material is transparent, dark, or somehow not efficiently pushed by radiation, then its behavior could deviate from expectations. In that case, 3I/Atlas might contain exotic components, perhaps the product of a different cosmic environment, making it a rare probe of conditions elsewhere in the Milky Way. The fact that the object displays repeatable, directional emission toward the sun suggests an internal or structural asymmetry, perhaps venting through a localized region. This could indicate that the physical conditions of the nucleus are asymmetric, or that volatile reservoirs are distributed unevenly. The implications of a true physical anti-tail extend far beyond mere curiosity. They force astronomers to question long-held assumptions about comet-like behavior and open the possibility that interstellar objects may not conform to the patterns we expect from solar system bodies. The appearance of multiple interstellar visitors, first Oumuamua, then 2I/Borisov, and now 3I/Atlas, suggests that our solar system may regularly encounter materials ejected from distant planetary systems. Each presents new puzzles, and each forces an expansion of our understanding of how small bodies behave under solar influence. In the case of 3I/Atlas, the sunward jet provides a rare and valuable opportunity to examine an object that contradicts our expectations at a fundamental level. Instead of reinforcing known models, it challenges them, and such challenges are vital for scientific progress. By studying this jet in more detail, astronomers may uncover new physical principles, new types of materials, or new dynamical processes that influence bodies traveling through interstellar space. As more observations accumulate, 3I/Atlas may ultimately force a revision of our understanding of comet-like activity in interstellar objects. Until then, the mystery of its sunward jet remains one of the most intriguing features ever documented in an interstellar visitor, offering a reminder that the universe still holds surprises capable of overturning even the most established scientific explanations.